Okay. I actually was very pleased with one thing. I found out that several people decided to buy Euclid. And if there is nothing else which comes out of the course, you know, I'm satisfied. So, by the way, here I want to stop and talk with just 1 second about if you decide to buy Euclid, which Euclid to buy. Okay, and first of all, you need to know about the following thing, that editions matter. And even the same edition could come in different versions. For example, I strongly recommend Euclid's translation by Sir Thomas Heath. There are several print-on-demand companies which sell it. Do not buy them, right? I mean, they're more expensive and very, very poor quality of things. There is a wonderful edition by Dover, which cost, the first volume cost $9, which should be within your discretionary budget. I don't think you need to ask your spouse. And it's in 3 volumes. Again, I don't know whether you should start with 3 volumes. I clearly suggest that if you decide to do it, at least buy the first one, because while everybody should aspire to work through all 13 books of Euclid, everybody must work through his first book, which ends gloriously with Pythagoras' theorem, with absolutely astonishing proof we might see during the second journey. A lot of historical material is, of which I will be talking and was talking last time, is covered in the wonderful book by the same fellow, Sir Thomas Heath, called History of Greek Mathematics, also published by Dover. 2 volumes. Again, you could start with volume 1 and maybe eventually get to volume 2. Just one word about Sir Thomas Heath. This is an example that even financial people could do something wonderful. He was a secretary of the British Treasury, and nobody would have remembered him now, but for the fact that every day he would go home and work on these wonderful books, which he will translate from ancient Greek and notate and do many, many things, right? So remember that even if you have full-time job in finance, you still could do something wonderful. So, you know, I feel very encouraged by his example. So now we will go back and look at the code. Some of you probably decided that it was going to be stories and stories and stories. Occasionally we'll have to read code. And today's lecture will start with code. And if we do well, I'll tell you a remarkable story later on, toward the end of the class. So, remember we started with fast multiply. And we wrote this code, and we looked at it, and we said, well, you know, it's pretty good because it does so many additions always, so many additions for odd bits. We came up with the formula, and we figured out that actually it's not optimal. Remember, it's not optimal. But it is very, very good. Then, of course, when we look at it, and even know anything about computers, we say probably it's not going to be as fast as we want it to be, because some of us will realize that a function call is actually an expensive operation. And right now, for every iteration, we do a function call. So, you know, it's really going to slow us down. There are some other infelicities which we're going to discover shortly. We're doing a little too much work, even ignoring recursion. Right? But again, let us look at this code. Now, how we're going to be looking at it, and this is sort of very often I get this question, so Alex, so how do you go about sort of, and the answer is very simple. You just modify and transform the code. You assume that whatever you wrote is bad. That's the fundamental assumption. I don't know about you, I never write good code. Well, at least not the first time, usually not even the second time. So rewriting and rewriting and rewriting, applying different transformations is the important thing which we need to habitually do. I often, now this is a little mini sermon, sort of I think that a lot of bad code comes from this idea of a single pass code writing. That you actually sort of, it's not a manly thing to do, to go back and change things. You have to just type it. It's a, write-only thing. And people, I actually see lots of code like that where it's very clear. The person started here, then after he reached, 30 pages down, because lots of code is, massive, he realized that everything in the beginning was sort of totally wrong, but he never goes back to rewrite, because that would be against the rules. So again, we have to learn to modify code. And again, you say, well, you're doing trivial examples. I don't know about it. I actually claim that everything we do is trivial little steps. We need to learn to decompose things into small components. Right? If you have more than 10 lines in a component, most likely you don't know what it's doing. At least I don't. Right? So let us try to use these transformations here. Transformation number one, and it's a very powerful idea, is it's often easier to do more than less. Room there? It's easier, for example, to write a function which is going to do some result plus NA, than to write a function which will do just NA. And it's a general thing. Always try to see if solving a bigger problem, it actually makes things easier. Right? It applies not just to software. For example, people who design hardware discovered exactly the same, literally exactly the same thing. Your broker is calling. No? What they discovered, that it's easier to construct, multiply, accumulate instruction than to construct, multiply, and accumulate. It's an easier task logically. So that's what we are going to start with. We're going to start with this familiar thing. Remember, we need to rewrite it iteratively. Sort of, we're going to introduce a more general function first. Instead of multiplying, we will try to do multiply, accumulate. My friend Paul McJones reminds me that the same thing applies in mathematics. It's very often easier to prove a more general form of a theorem than a specific thing. This is sort of, people think that abstraction costs. No, as a matter of fact, very often concreteness costs. Sort of solving an abstract general problem is often easier than solving specific problem. Okay, so let us go to multiply, accumulate. This is the first version. So we're extending the interface. So now we have A here as before. We're multiplying it by n, and we're adding it to R. So it's fairly straightforward how to do it. If n is 1, we are going to return R plus A. Don't forget, we're Egyptians. We don't have 0. So we don't have to worry about 0. We will learn about 0 shortly, but not yet. So then, if it's odd, we need to add A to accumulation, double A, and half n, right? Sort of, we are just, otherwise, if it's even, we do not need to add A. Accumulation does not change. The last bit is 0. We are halving n, the same thing, and we're still doubling. Observe, very, very symmetric code. Therefore, we could use this symmetry, and instead of 2 calls, have just 1. Right? We combine the calls. We just say that if odd, we will increment r. So now we actually got to the point where the code is shorter than what we started with. But nevertheless, and many of you say, well, and you see it's tail recursive, you could turn it into iterative thing. By the way, if you forgot what tail recursive is, I'll explain in a second. But before we do that, let us observe another very important thing which we need to do. This is a typical thing, and again, sort of, it's very clear that we're doing too much work here, because every time through the loop we're comparing n with 1. Do you agree with that? Yes? Every time. And every time through the loop we're comparing whether n is odd. But these are not two independent predicates. They do depend. Let me assure you that if something is not odd, if it's even, it's not equal to 1. We know that. So we should use this knowledge. Again, we always have to look for the dependencies. We forget to do that. Right? So let's not forget. So you observe that these two predicates are connected, and we have to find a way. It's a very simple way. We combine them. We first test for odd, because again, remember, n is going to be 1 only once. It's a rare thing. So it's usually false through the loop. Odd is sometimes true, sometimes false. So reordering them is always a good idea. Sort of testing the predicate, which is there is a chance which will be true, is something which should be done before we test something which is seldom the case. Of course, we always forget it, and we say compiler will get it. Guys, there are no artificially intelligent compilers. There are some optimizations which they do. Stuff like that, they often do not do. So we'll discover that we have to learn to do many compiler optimizations by hand. So, because, compilers, they're just programs. And they don't do what we can do. Let's hope that we're naturally intelligent. So, again, so what we observe is that we could combine these things into one clause, if clause, right? Test if it's odd. If it's odd, we increment. And then we test for 1. So every time n is odd, we're not going, every time n is not odd, we're not going to test for 1. We're skipping one operation through the loop. All right? Now, here we observe that this is now not just tail recursive, but it's only one recursive call. And a reminder what tail recursive procedures are. Tail recursive procedures are procedures which are recursive, but which return the value computed by recursive call without applying other operations to it. For example, our original function was not tail recursive. Where is the? You see, it's not tail recursive because we do recursive call here, but then we use the result, right? So we need our stack frame, in other words, because before we return, we have to do some more computation. So again, just quick reminder, this is tail recursive, and we could make it properly tail recursive. Properly tail recursive, where recursive call, which we make, looks exactly like the call to this function. It's R is R, N is N, A is A. Because then effectively, how we could transform it into iterative program? By just putting go to. If instead of this recursive call, we go to the beginning, if we put a label. Of course, you read someplace that go tos are harmful. They're not as harmful as you think. So, here it would be just wonderful if we put go to, it will work. But since they taught you that it's bad, we will rewrite it like that. We will not use go to, we'll say just while true. Right? And then, by the way, compiler will put go to. So don't get any ideas. So we consider go to harmful, but not the processes. They thrive on go tos. One of the major results, which older people might remember, by John Cock is every other instruction generated happens to be go to. Sort of, if you look at the compiler output, which I suggest you do periodically, lots of go tos there. So now we're almost done. We have iterative form. On the way of deriving it, by the way, we cut some complexity. We're doing fewer operations. But, well, we're not quite done. Because we didn't solve the problem which we started with. We didn't solve the problem of multiply. We wrote a more general function, multiply, accumulate, but we need to get multiply. It seems to be very simple. One easy way is to observe that if n is 1, when we just return it. Otherwise, we could split it into two parts. We could put n minus 1 as exponent or multiplier in multiply, accumulate, and 1a into the result. And it will be done. And again, it's tempting to stop here. So, it's good enough. I mean, and on the average, it's pretty much as good as anything else. Well, but we don't want to. One of the things, never stop when it's good enough. Let us spend just a little more time and try not to do extra operations. You see, for example, this one is going to suffer real badly if you start with the power of 2. Because instead of doing the power of 2, which would require just log n operations, it's going to split 1, drop 2, a number with all ones. Remember, numbers with all ones are particularly bad for us. And start doing it. So, it's not nice. Let's do something better. Again, we could do something better. You see, we observe the following wonderful property, that if n is odd, then splitting 1 is a good thing to do, doesn't cost us at all. Right? Because we're not getting any more ones in the exponent, we're just dropping 1 at the end. However, we know this wonderful property of every even number, except 0, that if you could keep dividing it by 2, it eventually will become odd. So we could start with a very, very simple loop that while it's not odd, double, half, double, half, double, half. Very, very simple loop. And then we're done. Well, except we're going to do an extra test. Where we're going to do an extra test, that's a very annoying thing. You see, we're calling multiply, accumulate. What is it going to do? It's going to test for odd, right? But we already know that we are odd at this point, because we're not going to get out of the while loop till n becomes odd. I mean, if I were not lazy, I would have written in assert here odd n, because you're not going to get out of the loop till n becomes odd. So we know that n is odd. And then multiply accumulate is going to do this one comparison. Say, Alex, you're totally mad. I mean, it's just one operation. Look, but I write code which millions and millions of people all over the world will use for millennia to come. Don't believe a word of it. But all of us have to aspire to that. Because you write some code. By the way, every time I wrote code and cut corners, that's the code which people are using. So you always assume that your code will remain. Even if you write something which you know for sure you're going to throw away, because that's the part which Ryan will pick and use. It's not necessarily Ryan, but what I'm just trying to say, we have to try to squeeze the last thing, because it's also simple and fun. Trying to make things right is fun. So what do we do? Since we know that it's odd, we do very, very simple thing. We peel out one iteration by, since we know that it's not even, we could half it right here, and we could double it right here, right? So we peel out one iteration. It didn't take much, but why not, right? So here we're in pretty good shape, actually, guys. This is as good as we could do, and it's not that bad because we're actually a little bit better than Knut at this point. Right? If you go, we're doing slightly fewer operations than he does, which it's always good. When you write something, go and compare yourself not with somebody you do not respect, but somebody who you do respect, like with Knut. Sort of always try to beat Knut. Well, worse comes to worse, if you don't want to aspire to that, try to beat me. That's doable. So what am I doing here? This is the next step of what we need to do with the code. I mean, coloring. It's obviously what I'm doing. I'm coloring the code. Why am I coloring the code? Because you see, I wrote the code here, and it multiplies integer n by integer a. It actually doesn't even do that. It multiplies int n and int a. Whatever int is, by the way, anybody knows what int is? Is a natural integer type of the machine, if you're lucky, by the way. Sort of, it's not always the case. So we don't even know whether it's 32-bit or 64-bit. It's something. On one compiler it will be one, on the other compiler it will be. Now they say, well, Alex, why don't you rewrite it as int32? I could do that. But then you see, maybe this code will work for you int32. Or maybe it will even work for you int64. So the interesting question is to figure out, when does it work? Right? Sort of after we, and this is 2 steps on designing a program. First step, you get the algorithm right. Right? You analyze all the dependencies, you get it right. So you get to this code. And then you start figuring out what are the types which I use and what are the operations I use. You say, well, I know that it's just 32-bit integer. You don't know anything of the kind because things change. If you want to design code which will survive, you have to worry about making it more general than just that, because things change. Yes, you know that certain things are never going to be greater than 32 bits, but you will be surprised. You would outrun of 32 bits. So let us look, plus again, what we will discover is there's a huge payoff. That if we do what I suggest that we do, if we color this stuff and spend some time thinking about it, this algorithm, which multiplies 2 ints, will be able to do some amazing things, like find shortest paths in a graph, or test large prime numbers for primality, or who knows what, or to do the, what do we call it, RSA. Right? So let us see what we do. So what I color blue everything which relates to R and A, because they are connected. It seems that there is a clear dichotomy here between red and blue code. That is, there is no place where we use N and A together. N and A and blue and red things are disjoint. Right? Like American politics. Very good. Very good. And they never talk to each other. So when we observe that, we could start figuring out what we could do. Sort of, and it's an interesting thing here, because what we do after we do the coloring, we look at it and say, what are the requirements on the corresponding things? So what is the requirement on R and A? Well, some very, very naive way of putting it, it should be plusable, whatever that might mean. Because that's the only thing which we do. We add these things together. There is a little bit more, but let us just for a second not pay attention to it. A little more is this. We're also returning it. And as we shall see in a second, it means something. But let's not see it. Let us be blind just for a little while. And then red things, we don't add red things together. We have a very simple operations on red things. This is, we check whether it's odd, and we compare it with 1, and we half it. It's a halfable thing. Whatever, yeah. Okay, so these are the only operations we do on red things. And it's a very, very important insight on both, because eventually it will allow us to produce so much more useful code right out of this. So let us do the first step. Again, the first step, I just syntactically separate them. I say, well, I need one type for A and another type for N. And, this very convenient way of doing it for A, I'm going to use capital A because, why not? And for N, I'm going to use capital. I know nothing about them. This is just strictly syntactic analysis. Right? So I do this, and then now the problem becomes immediately much simpler, because instead of trying to figure requirements on this whole function here, I need to figure separate requirements on A and separate requirements on N, since there are no cross requirements. Right? So whatever these requirements are, they are disjoint, which is very, very handy. And you always start with the simpler one. Which is simpler one? A is simpler. It's just plusable. It's just one operation. We start with plusable thing and see where we get. So the syntactical requirements are that we could add it together. It could be passed by value. You see, we are passing it by value. And what does it mean that we pass by value? It means it could be copied. There is a copy constructor. You say, well, there is always copy constructor. First of all, it's not true. There might be types which do not allow you to copy. And then there is an assignment. So these are the only assignment. Just for those of you who don't believe me, that's assignment. Right? This is assignment. So these are things which we need, plus assignment copy constructor. Nothing else syntactically. But you see syntactic requirements, and that's a very important thing that people say, well, we're done. We'll call it plusable, assignable, and constructible. Well, you know, and is it all right if plus is going to do division with remainder? Is it all right if assignment is going to zap everything and make it to 0? Or do we have some semantic constraints? Well, obviously we do. We remember one semantic constraint from early on, from the way we obtained our piece of code. Remember when we were deriving our first recursive algorithm a week ago, we started with important property which allowed us to do it, associativity. That is, this piece of code makes absolutely no sense unless plus is associative. Right? So that's our basic requirement. And this is, I just want to show off how well I could do things in LaTeX. Again, you know, I spent a lot of time doing these slides, and they're all done using 2 different technologies. Sort of all the pictures and simple words are done in PowerPoint. All the beautiful mathematics is done in LaTeX. So for which I need to be congratulated. So we know that it is associative. But here we get to a problem which people often forget. Well, first of all, things are not as associative in computers as we want them to be. First of all, mathematicians, being naive people, they assume that plus is a total function. What does it mean it's a total function? It means that whatever 2 things I give you, you could add and get a result. It's a function. Sadly enough, it is not true in our world. We live in a world where some things are plusable and some things are not plusable. You could overflow. You could just, the function is not defined. And some of you might even know associativity sometimes might not hold. Right? Especially when we deal with doubles. And especially if, sort of in an easy way of seeing it, imagine that we have a humongous number, and we add humongous number, and we subtract humongous number. If we do humongous number plus humongous number, we will overflow, and subtract, will be a bad situation. However, if we do subtraction before we do, if we regroup, we will get some potentially meaningful result. So associativity might not quite work. So the important thing to remember that it does not defeat our purpose. What we say that our function makes sense only for as long as these operations are defined. You have to understand they're not always defined. A multiply function will not always work. Things might overflow. This is perfectly all right. Partial functions are all right. They're not the end of the universe. We just need, again, for a rigorous treatment of this issue, again, those of you who have elements of programming might want to look at it. Those who don't, I still have a pile of books, which, you know, I'm surprised. The price is very good, you know. It's $0.00. So, and it hurts Paul and my ego immensely. There are 2 authors which are giving away a book, and nobody would even bother to ask for it. For $14. Well, I'd rather you picked it up in my office. And moreover, there's absolutely no way Paul and I could sign the Kindle edition, right? And some of you who obtain free edition in my office could also obtain. So I mean, my signature is, worth nothing. You could always get it, but Paul's signature is really valuable. So okay, so there is a rigorous treatment there, and then there is an enormous amount of requirements, which comes with the notion of construction and assignment. Because what we did not see is something which is behind construction and assignment. Our code nowhere used equality. Well, it's not quite true. Our semantics, by the way, did use equality right here. Right? So even semantics of plus cannot be expressed without equational axioms. Actually, equational axioms are sort of the basis of mathematics. But even if you don't do things like associativity, you absolutely have to decide what equality for your type means, because otherwise you cannot know what copy construction or assignment is. Because, simply speaking, what is a copy? Copy is something which is different but equal. So you have to define equality. You have to know what equality is to define copy. And what is assignment? Assignment is something which makes its right side equal to its left side, equal to equality. So behind all of that, I'm just showing you in the simplest piece of code how much we need to build up to do it right. So we need a notion of equational reasoning to deal with any axioms. And what is equality? By the way, here I have to say certain things which, if I were talking to a bunch of mathematicians, they wouldn't even understand what I'm saying. I have to say inequality is negation of equality. So why do I have to say it? Because you see, I'm an old guy, and during my long life, I had to deal with different bodies, like standard committees. And a long time ago, about 20 years ago, I tried to convince this august body that, exactly that inequality is negation of equality. They unanimously defeated it. They said that will constrain programmers' freedom. We want Ryan to be able to define equality to do something, and inequality to do something completely different. Observe, you could do it. You could just define inequality to do something else. The argument is that we want Ryan to be free. Well, as a matter of fact, we don't want Ryan to be free. We want to constrain our equality to preserve our freedom. Because if Ryan starts doing crazy things, it makes us his slaves, right? Of course, it does. There is a great thing for Ryan. I mean, job security. Because, if you define inequality to do multiplication, and Bill decides he doesn't need your services anymore, well, bad things will happen because, it's really hard to change. So, very important thing is once and for all of us, to decline this offer of freedom, to say never in our lives we will define inequality to do anything but negation of equality. And then again, we're not free to decide what equality means. Equality, sort of our freedom is illusory, because there is this wonderful thing which has been known to philosophers and mathematicians for centuries. And when we define equality for our types, we better do what they have been doing, again, unless we want job security. And again, job security is an illusion, let me tell you. So you cannot obtain it even when you write bad code. I shouldn't be telling them things like that. So what do we know about equality? It better be reflexive. Everything has to be equal to itself. Well, of course, some of you will say, but, could you step into the same river twice and all of that? Let's leave it to ancient Greeks. In our world, we can. A is always equal to A. Then, if A is equal to B, it's better be true that B is equal to A. Symmetry and transitivity. Right? These are fundamental things. But that's not enough, because there are many other equivalence relationships. These three axioms give you what is known as equivalence. We want a much stronger thing. We basically want substitutability. We want, for any predicate, and this is second order axiom for those of you who know. For those of you who don't know, it's all right. For any predicate P, we wanted that if A is equal to B, then this predicate will evaluate to the same thing, right? But in some sense, the equal things should be substituted in work. It's actually very complicated one way again. For the formal treatment of all of that, elements of programming, I cannot do it completely here, and I will not, even during all the four journeys, because obviously in computers, things are much harder. Think about, for example, address function. Right? So there are things which are not equal for equal things. If equality of addresses is not implied by equality. Two integers might be equal, but live at different addresses. Yeah, but nevertheless, we still need to have equality. I'll just give me 1 second. I know we have to have a break. There is a fundamental notion which some of you might have heard. I know that John, for example, knows it well. Notion of a regular type. He gave a type where construction, assignment, and equality are connected. In other words, a type where if you make a copy, you get an equal thing. If you assign, you get an equal thing. Right? If you do default construction followed by assignment, it's equivalent to doing, it's basically sort of, it behaves in a regular way. So the assumption for everything which we will be doing in this class is regular. Just a little bit more. So regularity is the default. In general, you should always try to make things regular, but it's not always doable. So there is an interesting problem 70. Figure out, this is homework, you don't do it in the class. There is a case in our basic type system, in C, not even in C++, where fundamental equational axioms are broken. Figure out what it is. Figure out what to do about it. You say it's an open-ended. Yeah, it is an open-ended. It's a little research problem, but you could do it in a week. There is another more interesting thing related to regularity. Some of you might have heard of constructible reals. This is a data type which allows you to have real pi with all its full glory, infinitely many digits. So there are implementations of constructible real. Sort of a best one, in my opinion, is done by my friend Hans Bohm. For those of you who really want to play with it, there is this remarkable calculator where you could do calculation with real numbers. Pi goes on forever, except for his user interface. It sort of stops at about 300 digits. But the underlying implementation goes on forever. He's not very good at doing UI. So try to analyze that. Then we'll have a break and we will continue.